Okay, guys, sorry about that. Okay, so anyway, diagonals bisect one another on a trapezoid. I'm sorry, on a parallelogram. So like this line and this line actually cut each other in half. So the interesting thing you're going to see here is now some overlap. So diagonals bisect each other, copying, for a parallelogram, and of course then push to its three offspring. One here for rhombus, one here for rectangle, and then one here for square. Now, on these three though, because they also share, at least these two, rhombus and square, since they share an identity with kites, since we kind of see kites come through here, I erase that, and push to rhombus. Um, Rhombus and square already has something like that. I mean, check this out right here. One diagonal bisects the other, one diagonal bisects the other. But now we have diagonals bisect each other. We don't really need to list both. So what I mean by evolution, I mentioned that before, is that we started out with just one diagonal bisecting each other, but now we can say more specifically diagonals both bisect each other. And so we can actually back down on this definition for rhombus and square. We don't need to mention that one diagonal bisects each other because now they both do. It's kind of redundant. And again, with properties, we don't necessarily have to list them all. It's just that we want the ones that make the most sense and are applicable here. And so that's when some of this sharing kind of helps us take down the list a little bit. Right? So this should be down here with rhombus. Boom. Okay. So that's pretty much it for parallelogram. Let's talk rhombus and let's talk rectangle, and then we'll call it a day. So let's talk about a rhombus. Let's talk about the picture of a rhombus. All four sides are the same. 1, 2, 3, 4. And so there's a lot here that we already mentioned. All the angles add to 360. All the diagonals actually bisect each other, which is true. Now I'm not claiming all the sides are the same. They just bisect one another. That's one I just picked up. It says right here the diagonals intersect perpendicularly, and that's true. You have one set of opposite parallel sides. Now here's where we can actually evolve this. Because it's no longer true, it's just one set of opposite parallel sides. We have actually both sets, so we can actually change this to both sets because we got that directly from parallelogram. Two sets of consecutive supplementary angles, that's still true because just like the parallelogram, like these two would be supplementary, two at the top would be supplementary, those would be supplementary. Opposite angles are congruent, opposite sides are congruent, which is still true. Diagonals bisect one another. There's actually nothing to add here. And so that's kind of the cool part about all these properties is that now at the end we're looking at the higher shapes. There's nothing else that makes them special. The definition makes all the sides the same. We have both sets of sides congruent. But that's all I got to say about a rhombus. That's done. Let's talk about a rectangle. Of course, we have the definition. All the angles are 90. When you think about a picture of a rectangle, let's start putting in some of the properties that we already know. Two sets of consecutive supplementary angles. Well, that's got to be true since they're all 90s. Opposite sides are congruent. That's something we wanted part of the definition initially, but it turns out to still be true because of a property. Opposite angles are congruent. Diagonals bisect one another. Let's put that one in. Okay, so if I have this diagonal, it is true that they bisect one another. And really, guys, that's all I can say about a rectangle too. Like, there's nothing else that's special. They don't intersect at 90, but you didn't expect them to because they were not connected to a rhombus. The opposite angles, opposite sides are parallel. That comes from the definition of a parallelogram. So I suppose we can put that here. Two sets of parallel sides. And that's it. So we're pretty much done with rectangle too. So all the work we did up here in the tree has filtered down and actually gave us some nice definitions here as well. So again, from the parallelogram, we have two sets of parallel sides. But when you think about a square and draw it out, well, we know these are 90. We know these are congruent. Therefore, they have to add to 360, so I'm good there. Diagonals intersect perpendicularly, so diagonal and diagonal. intersected at 90. One set of opposite angles congruent, opposite congruent angles. Again, I think we can evolve that a little bit, just like we did for rhombus, and let's write both sets, or two sets, of opposite angles are congruent, which makes sense since they're all 90. Two sets of consecutive supplementary angles, again, that makes sense, they're all 90. Opposite sides are congruent, had that covered by definition. Opposite angles are congruent, had that by definition. Diagonals bisect one another, which is also true. And so again, just like with rectangle and rhombus, I can't add anything to the property list. It's already done for me. And so that gives you a sense, hopefully, of kind of like why we're talking about the family tree. It's because these things are so interrelated. Like, it's important to note that if you know just a little bit about one shape, you know a lot about all the shapes. Guys, that's all I got for you. Thank you for bearing with me. Thank you for taking these notes. This is kind of like a supplement to the notes up here, so no properties needed, or no, sorry, no summaries needed. But you're welcome to go back, and if you want, rewrite your summary and repost it if you want to do that. So now you have a bigger picture of the tree. All right. So guys, that's that. Thank you for listening. I'll see you guys later.